In this video, we're going to be looking at scientific notation. So if you've watched the PowerPoints, what you've learned about scientific notation is it's a way to express either really small numbers or really large numbers by using exponents. So when we talk about exponents, we usually write scientific notation where we're taking times 10 to the something. Now we're raising 10 to the power. This power is called the exponent. Okay, so how do we write scientific notation? Well, like everything we've been looking at, there's a set of rules to go through. So let's look at those rules and apply it to these examples here. So what I have here is I have a list of numbers written in normal notation. So by normal notation, what I mean is how we write numbers usually on a day-to-day basis, because we usually write them decimal points, commas for big numbers, so on and so forth. So we're going to transform these numbers from normal notation into scientific notation using the rules over here. So let's look at the rules. Now, before I start applying the rules, what I want to do is I want to count my significant figures. So the reason we learned about significant figures first is because we're applying it not only to calculations, but also to these transformations between normal and scientific. So the reason I count my significant figures first is because once I start moving decimal points around and changing things, I'm going to lose track of what my original number looked like. And then that might confuse me as to how many significant figures my original number had. So by counting the significant figures first, I avoid that confusion. So let's start with this first number. So we have a decimal point number, 0.0024. So counting the significant figures, remember from our rules with sig figs is that we can't start counting until we get to our first non-zero number. Okay, so I have a 0, a 0, a 0. So none of these zeros count, even though there's a decimal point, because I can't start counting till I get to my first non-zero, which is the 2 in this case. So the 2 is my first significant figure. The 4, since it's a non-zero number, is my second significant figure. So this normal notation number has 2 sig figs. Now, once I'm done converting this normal notation number into scientific notation, my very last step is to check my significant figures. You can see number 3 down here to make sure it remained the same. All right, so let's start. Rule number 1, to convert this, or change this, I should say, to scientific notation. It says we want one SF, which is a significant figure, meaning a non-zero number, to the left of the decimal point. So if I want just one non-zero number to the left, where is my decimal point going to move to? Well, it's going to move between the 2 and the 4. Because if I put my decimal point here, what I now have is just one significant figure, or one non-zero number, to the left of the decimal point. So this is where I want my decimal point to be. Okay, so I'm going to write that over here where I have 2.4. Okay, now I need to figure out the exponent part. So I can write times 10 to the, and then now I need to figure out what the exponent is. So number 2 tells me how to do that. It says the exponent is going to equal the number of times you have to move the decimal. Okay, so my original decimal point is here in blue. I want to move it so that it's between the 2 and the 4. So to get it between the 2 and the 4, how many times do I have to move it? I have to move it 1, 2, 3 times to get it between the 2 and the 4. So that means my exponent's going to be 3. I'm not done yet though, because I need to check and see, okay, should it be a positive exponent? Or should it be a negative exponent? And there's 2 ways to look at this. So it's going to remain positive, so it's going to be a positive 3 if the original number in normal notation is greater than 1. Was my original number greater than 1? No, it was not. It was less than 1. It was 0.0024. Now it'll be negative exponent if the original number in normal notation was less than 1. Was my original number less than 1? Yes, it was. Now, some people prefer, instead of remembering this greater than 1, less than 1, they prefer to remember it in which direction they moved the decimal. So in this case, we moved the decimal 3 times. What direction? We moved it to the right. I just realized I had this wrong. So if you have to move it to the right, it's going to be a negative exponent. If you have to move it to the left, it's going to be a positive exponent. Now you can obviously see from my mistake here that I remember it the greater than 1 and less than 1 way. Okay, but whichever one sticks in your head better will work just fine. So now that we have the rules adjusted correctly, let's try the next one. We have 0.0180. Okay, start by counting significant figures. So we start counting at our first non-zero number, so we're going to start counting at the 1. The zeros before the 1 don't count. 8 counts, and now this trailing 0, it does count. So why? Because there's a decimal and we already started counting. So we have a total of 3 significant figures for this guy. Next, let's figure out where the decimal should go. So the decimal is currently here, but where we want it to be is so that there's 1 significant figure to the left. So in order to do that, I'm going to put it between the 1 and the 8. That way I have 1 non-zero number to the left. That's going to give me 1.8 times 10 to the. Now next I want to figure out my exponents. So to figure out the number itself, it's how many times we have to move the decimal to get it from where it originally was to where we want it. So we have to move it 2 times. So my exponent's going to be 2. Now I need to figure out if that exponent's going to remain positive or if I need to add a negative sign to it. Well, I moved the decimal to the right, so that means moving it to the right, it should be a negative exponent. You can double check that by seeing the original number was less than 1, right? It was 0.0 something. So it fits both criteria. Now, you don't want to skip the last step. I know I skipped it up here, and that could have been a bad mistake. I ended up having the same amount of sig figs, but that was luck. So looking at this one, you want to check to make sure the significant figures remain the same between the two. And when I'm talking about significant figures, we're just looking at the numbers before this multiplication sign, okay? The exponents and the 10 to the doesn't count towards sig figs, just everything before that multiplication sign. So here, the original normal notation, I said I had 3 sig figs. That 0 counted. But notice when I wrote it in scientific, I left the 0 off. So this is showing right now that I only have 2. 1, 2. So I need to make sure that I am including that 0. It mattered over here. It still matters when I'm writing it in scientific. So it would have been incorrect if I forgot that 0. So just make sure you're double checking your significant figures. So this would be the correct scientific notation of that number. All right, next problem. We have 673,000. So this is a very large number, right? So first thing we want to do is count the significant figures. We start counting at the first non-zero number, which is 6. The 7 counts and the 3 counts because they're not 0. So the hard part is figuring out if the zeros count. Now zeros can count in 2 different scenarios. Scenario 1, if the zeros are between 2 non-zero numbers, which they are not, right? There's no non-zero number on the other side. Or if there's a decimal and we already started counting. Okay, well in this case, is there a decimal? No, there is not. There's a comma, but a comma is not a decimal. So since there's no decimal, these zeros do not count as significant figures. So we have 3 total significant figures in this number, which is helpful to us because when we write it in scientific notation, since those zeros don't count, we don't have to write them. Okay, that's going to save us a little bit of time and room. So now that we know how many sig figs, let's figure out where our decimal point should be. Remember, we want just one non-zero number to the left of the decimal. So that means it's going to go between a 6 and a 7. So I'm going to get 6.73, and I'm not going to include the zeros because I just said they didn't matter, times 10 to the, okay? Now we need to figure out the exponent. So we need to figure out how many times we have to move the original decimal point to get it between the 6 and the 7. But I said in the beginning, there's no decimal point in this number. So where do we start? Okay, if you don't see a decimal point in the normal notation form, that means you start at the end of the number. Okay, so we're going to start here at the end of that last 0. So to get it all the way between the 6 and the 7, we have to move that decimal 1, 2, 3, 4, 5 times. So my exponent's going to be a 5. Now notice this time I moved to the left. So that means my exponent is going to stay positive. Also, my original number, 673,000, it was way, way greater than 1. Okay, so another tip of the hat to the positive. So this would be the correct scientific notation. You can double check the sig figs. I have 3 in the original number, and I still have 1, 2, 3 in my scientific notation form. Now let's look at 1500. Notice this time there's a decimal point at the end. Why is that important? Well, it's important for counting significant figures. So I start counting at the 1. I know the 5 matters. Now figuring out if the zeros matter is the hard part. And the very last rule we looked at with significant figures was that if there's a decimal, which there is, and we've already started counting going left to right, which we have, then yes, the zeros matter. So in this case, yes, they matter because of that decimal point. They didn't matter up here because the original normal notation number didn't have a decimal point in it. We added a decimal so that we could figure out how many times to move it. Okay, so in the 1500 with a decimal, we have a total of 4 significant figures. So this gives me, I skipped a step. I need to figure out where my decimal point now should be. Okay, so this is rule number 1. I want one non-zero significant figure to the left of the decimal point. So my new decimal point, instead of being here at the end of the number, I'm going to want it between the 1 and the 5 so that I have just one significant figure to the left. So that gives me 1.5. Since the zeros mattered in the normal notation number, they also matter in the scientific notation. So I want to include them in this case because I want to stay at 4. Now for the exponent itself, how many times do I have to move that decimal? 1, 2, 3. I move to the left, so it stays a positive 3. Checking sig figs, I got 4 and 4. Good. Now let's look at the next one. So some people have trouble when the decimal is randomly in between non-zero numbers. So let's look at how we approach this one. First, starting of course with how many significant figures there are. So all of them are non-zero, so all of them matter for a total of 3 significant figures. Figuring out where the decimal point goes, we don't want it here because here we have 1, 2 significant figures to the left. And we don't want 2, we want just 1. So we want to move the decimal point between the 1 and the 3. That's going to give me 1.32 times 10 to the, to figure out the exponent, we start at the original decimal point. How many times do we have to move it? Just once in this case. Next, we want to figure out if that stays a positive or if it needs to be a negative. Well, I moved to the left, so it's going to be positive. Also, my original number of 13 was greater than 1. Okay, so this would be the correct answer. 3 sig figs here in the normal notation form and 3 sig figs, in the scientific notation form. Now this last one is very tricky. Why? Because of this negative sign. Okay, that kind of throws people when we talk about the exponent portion of it. So let's look at this one, starting systematically by counting our significant figures. Now remember, when we count significant figures, it doesn't matter if there's a negative sign or not. We're just looking at the numbers themselves. So we start counting at the 2. The 9 matters, the 7 matters. Does this 0 matter? Yes, it does, because there's a decimal and we already started counting at the 2. So we have 4 sig figs here. We don't want the decimal point between the 9 and the 7 because that leaves 2 non-zero numbers to the left. So we're going to move it between the 2 and the 9 instead. So when I write it over here, I'm going to go 2.97. A lot of people stop there, but you don't want to because remember, we said this 0 mattered, so don't forget to include it. Now, I want to just carry over that negative sign. Okay, I don't have to do anything to it, but it is still a negative number. Now to figure out the exponent, it's how many times you moved the decimal. So we started between the 9 and the 7, that's the normal notation, but we want it between the 2 and the 9. So to do that, once again, I'm just moving it once. Which direction did I move? This is the tricky part. I moved to the left, right? So if I move to the left, that tells me it should be a positive exponent. Okay? And it should be, that's correct. But if you memorize it this way, where if the number is greater than 1, it's positive. If the number is less than 1, it's negative. Well, a negative number is less than 1, right? I mean, 0, and then you go to -1, -2, -3, so that's going to be less than 1. So if you're memorizing it using this, you want to make sure if there's a negative sign that you're not counting that towards the number itself. So what I mean by that, I'm going to go ahead and change this rule or put a stipulation on this rule. So instead of being less than 1, you want to make sure that there is more than one number to the left. So what I mean by that is your exponent's going to be positive if there's more than one number to the left of the decimal point in the original number. Okay, so in all 4 of these cases, ignoring negative signs, right, the original decimal point, there was more than one number to the left. So that means all of these exponents stayed positive. In these top 2 cases, we have negative exponents, notice. That's because there were no numbers to the left of the decimal. Okay, so there's lots of ways to remember this. And if that didn't jive with you, just if moving to the left, moving to the right makes more sense, forget this and do it that way. Both ways work. Okay, so what I want to do next is we have looked at taking normal notation numbers and changing them to scientific notation. I want to do the reverse direction. So we're going to put up some scientific notation numbers and we are going to write them in normal notation. Notice these are all scientific notation. How do I know that? Well, first of all, not only are there exponents, but notice for every single one of them, there's only one non-zero number to the left. One non-zero number to the left. Okay, so these are correct scientific notation forms. We are going to now change them and see what they will look like in normal notation. So for normal notation, we have 7.80. Okay, we're going to approach it in a similar way by counting our sig figs first so that we know how many should be in our answer. So remember, for sig figs, when it's in scientific, we're looking at just the numbers before the multiplication sign. So we have 7 in the 8 count, and this 0 counts because there's a decimal and we already started counting. So a total of 3 significant figures in that guy. Now, to figure out what it looks like, we're going to use the exponent to figure that out. So if the exponent, in this case, is negative, we're going to be moving the decimal point to the left. So it's the opposite. When we're going from scientific to normal, it's the opposite of when we went from normal to scientific. Okay, so what I'm saying is if you have a negative exponent, you know this needs to be a small number. So in order to make it a small number, you're going to have to move it to the left to make it smaller. How many times to the left? Well, that's what the number itself tells you. 2 times in this case. So moving that decimal 2 times to the left. 1, 2. My new decimal point's now here. But notice I have an empty space. What are we going to put in the empty space? A 0. So our normal notation form becomes 0.0780. Now I always want to check my significant figures at the end. So to check my significant figures, does this 0 count? No. Why? There's a decimal point there. You'd think it should. But it can't count because I haven't started counting yet. I start counting at the 7. The 8 matters, and then the 0 after the 7 and 8 does count because there's a decimal and I already started counting. So I still have 3 sig figs, so that checks out. That's my correct answer. Looking at the next one, we have 5.2 times 10 to the 5th. Now, to do this one, let's start by counting our significant figures, both non-zero numbers, so that's 2, means we want 2 in our answer. Now we know we need to move that decimal point to get it in normal notation, but what direction? Well, we look at the exponent to figure that out. So I know I'm going to have to move it 5 times. Since it's a positive exponent, that means this number is going to be a big number. So if I want this number to get bigger, which way do I want to move the decimal? Going to want to move it to the right. I want it to get bigger, right? How many times to the right? 5. Now when I move it 5 times to the right, I have 1, 2, 3, 4 empty spaces. So to fill in, I need to put zeros in each of those. So I'm going to do 0, 0, 0, 0. Okay, now that looks a little messy, so let's rewrite it over here. So I know I have the 5 and the 2, and then I'm going to have 1, 2, 3, 4 zeros after it. Now, I don't want to keep this decimal point here. If I kept that decimal point there, what I'm saying is, hey, those zeros now matter. But I don't want them to matter when I'm counting sig figs because my original number had 2. So I only want 2 in my answer. So the correct answer is going to be 520,000 in normal notation. And only those 2 numbers are significant. The zeros are not because there is no decimal. Let's move on to the next one. 1.9000 times 10 to the 3rd. Counting the sig figs, 1 and the 9 count. Do these 3 zeros count? They do, because there's a decimal and we started counting. So we have 1, 2, 3, 4, 5. 5 significant figures. So I'm going to want 5 in my normal notation as well. Now I need to figure out what the number is going to look like. So I know I'm going to have to move that decimal that's right here between the 1 and the 9. I'm going to have to move it 3 times. Since it's a positive exponent, this number needs to get bigger. So for it to get bigger, I'm going to move it 3 times to the right. So my new decimal is now between these 2 zeros. So I have 1900, then the decimal point, and then another 0. Notice I'm sticking with 5 sig figs. All these zeros count because there's a decimal point and we started counting at the 1. Next, we have 3.0 times 10 to the 0 power. So we might not have seen this yet. So let's just approach it like we would any other, even though it looks a little different because of that exponent of 0. We're going to start by counting our sig figs. There are 2. Now the exponent tells us how many times to move the decimal. Well, the exponent's a 0, so what does that mean? We move the decimal 0 times. So the normal notation of this number would just be 3.0. It's kind of a trick one. I have one more that I want to try because I want to throw in a negative because these tend to kind of throw people through a loop. So here we have a scientific notation, but it has a negative sign. Anytime we have a negative sign when we're going between scientific and normal, ignore it when you are going through your steps, but don't forget to include it in your final answer. Okay, so let's approach this like it doesn't have a negative sign. Let's count our sig figs first. This last 0 does count because of the decimal, and we already started counting for a total of 3. How many times do we move that decimal point to get it in normal? Well, we're going to move it 3 times. What direction? That's what the sign of it tells us. In this case, it's a negative sign, so that means that this number, 6.2, needs to get smaller. So in order for that number to get smaller, we want to move the decimal to the left. How many times? We just said 3. So we get 1, 2, 3. So we're going to put zeros in these empty spaces. Here's where our new decimal point is. So when we write this out, we want to make sure we include the negative sign, even though it didn't factor into our converting it to normal. And then we write the number just how it's written here. So we have the decimal, 2 zeros, a 6, a 2. We are keeping that last 0. So this would be the normal notation form of that guy. Now, if you want to check your sig figs, by all means do so. We said there were 3 over here. When we're counting sig figs, we can't start counting till we get to our first non-zero number, which is the 6. The 2 counts, and then the 0 after the 6 counts because we already started counting.